we can see loading at Clemson, and now Clemson can see it.
Okay, thank you. Okay. All right, my name is Josh Kember. I'm the lead structures engineer for Team 4. Our UAS is called Savior. Our team is comprised of students from Purdue, Georgia Tech, and BYU, and we're grateful for you guys to be here and listen to our presentation. So this is an agenda of what we'll be going over today. You're going to have the opportunity to hear from myself, Nick Wallace, and Pratik Chamakura, and we're looking forward to sharing this with you. So for our mission, just a restatement of what our mission is Savior is a search and rescue drone UAS that will be deployed approximately 2 kilometers from environments that are affected by hurricanes or floods. From that deployment area, Savior will fly to climb to an altitude of 50 meters, where it will then cruise to a search area and perform a predetermined search pattern, searching for people in distress. As it searches for these people, a camera on board with an image recognition software will search for these people, and once it locates these people, it will transmit that data back to a ground station by sending both GPS locations and an image of that area. So from the MCR, there were a few concerns that we were able to resolve. Currently with stakeholders, we were asked to reach out to individuals who were affected by recent hurricanes, and we're in the process of doing that. We've made phone calls and sent out emails, and are just waiting back for that. We're also asked to make some more definable mission objectives, and so that being said, we were able to define a flight endurance of 60 minutes and a range of 50 kilometers. As for mission altitude, we think that 50 meters is optimal in studying different camera capabilities and being able to resolve people who are in distress. For camera and image processing, Nick Wallace is going to discuss that further into the presentation. And for weight, we were able to reduce the overall weight from 15 pounds down to 12 pounds, so we're pretty pleased with that. Our team was able to come up with several trade studies, and these trade studies were graded based on different criteria. You can see the grading criteria for each trade study listed there. These are our figures of merit that we were able to determine a result that we think will be useful in these designs. And several of these trade studies will be expanded upon in the presentation. So I'd now like to turn the time over to Nick Wallace.
Awesome, thanks Josh. So for the next part of our presentation, we're going to be talking about payload specifications. And the content and these slides were created by our teammate Andrew Arlarcone, who unfortunately is in a class right now. So I'm going to be presenting instead. But this is a flow diagram showing the processes on board our aircraft. So the blue rectangles in the middle represent where data is being processed, and data flows from the sensors to the CPU and the PixHawk, where data is shared between both of those components. And then the controller will be sending out data to the aircraft controls and to the ground station. So as previously stated, a big part of our mission is to have our aircraft autonomously recognize people that are stranded. And so we started looking into how to detect people in real time. And we found that the ideal solution is using pre-trained models, which are trained with large pre-labeled data sets to identify multiple objects such as like people, cars, or animals. So these models, they require libraries for computer vision and machine learning to access videos and to function and operate properly. And all of the pre-trained models that we were looking at can run off of the CPU, but we also found out that they can run with a CPU and a GPU or a graphics processing unit running in conjunction. This greatly increased decreased the processing time per frame by almost an order of magnitude. And so as we were analyzing our mission and understanding that we were going to be processing live streaming or live video, we decided that this CPU with a GPU acceleration was optimal for our mission. So the only caveat with using GPU acceleration is that a GPU needs to be able to support parallel computing libraries such as CUDA or OpenCL. And as we were researching, we found that CUDA is far superior in performance and functionality over OpenCL, and it also seems to be the most popular among programmers. And so we decided to look further into CUDA, and really the only downside to using CUDA seemed to be that it only operates and is compatible with NVIDIA GPUs. And so that narrows our selection options for GPUs, which I'll talk about in a future slide. So this slide is meant to demonstrate that there is a balance between computational cost and then accuracy in the pre-trained model in identifying objects in the video. And so as we were looking into our pre-trained models, there's this balance between how long does it take to process the frames and then how accurate was it in actually identifying objects. And so two pre-trained models that we specifically looked at was the Yellow V3 and the RCNN. Within the Yellow V3, there's two divisions. There's a tiny Yellow V3, which only requires about 30 megabytes to run, as opposed to the standard, which takes about 200 megabytes. But as you can see from this image here, it wasn't as successful in identifying every single person, even though it did take less computational power to run. The RCNN also has two divisions. There's Inception V2 and NAS. So the Inception V2 was a little bit faster. The two divide up the image in different ways, which differs the computational time involved with both of them. And so it seemed like both of them were fairly successful in identifying objects, and the Inception V2 was faster. And so this was just a video that we downloaded off of YouTube, and we wanted to get some data that would more closely resemble what type of video we'd be seeing on our aircraft. So this is actually on the 4th floor of Georgia Tech, and we looked at both of these pre-trained models. And as you can see, the tiny Yellow V3 was completely unsuccessful in identifying any of the people walking. The faster RCNN and the NAS were both pretty successful, and the Yellow V3 seemed like it was able to ping every single person in the image. And so as we were comparing the two, even the faster RCNN, the Inception V2, was slower than the Yellow V3, and the Yellow V3 seemed to be more successful in identifying the objects. And so it seemed like the obvious choice for our mission was to use the standard Yellow V3. Some other features involved with it was that we were able to train this model, and so we could optimize our results for aerial shots or for other camera angles that might be more specific to our mission. And so from here on out, we're going to be looking more into the Yellow V3. So as I mentioned previously, with CUDA, it's only compatible with NVIDIA processors. And so we looked into 3 NVIDIA processors, and it seemed like the perfect compromise for cost and processing power was the TX2, which is around half of the price of the AGX, but only for about a quarter of the price. So the only caveat with using the TX2 is that it requires a $300 expansion board, but even with that additional cost, it's still only about half the price of the AGX. And so we thought that this was a good decision for our UAS, and we're going to be using the TX2. We also have been reaching out to a lot of vendors. We've been having some issues actually getting responses from them, but we've called and emailed multiple times the companies in the white bullet points right there. And so as soon as we hear back from these vendors, we're going to start weighing the pros and cons of each camera based on our mission requirements, and we'll be looking at variables such as price, field of view, and resolution. This is our finalized design requirements. It's, for the most part, just a continuation of the slide that we presented in the MCR. The only 2 that we added was number 7 and 8 because we felt like we needed more definable objectives. So number 7, our UAS will cover a 1.5 kilometer by 1.5 kilometer search area. And then we want it to be able to remain in flight for an hour or a minimum of 1 hour, as Josh specified earlier. And so with that, I'm going to turn over the time to Pratik to talk about our aircraft configuration and aerodynamics.
Hey, thanks, Nick. This is Pratik from Purdue University, and I'll be going over some of our configuration selections for our aircraft. One of the defining changes that we've made from MCR to PDR was in the change of the wing measurements. Originally, we had a very large wing, which we deemed was unnecessary for the speed we wanted to fly at, which is about 15 meters per second. So we downsized the wing a little bit, which helped reduce our weight and also allowed us to carry a heavier payload, which we now know is a CPU plus GPU combo. So that worked well for us. Next slide, please. So this is where we started with our constraint sizing. Two of our major constraints were that it had to be hand launchable at about 8 meters per second, and the second being we wanted an efficient cruise at about 15 meters per second. The solutions we kind of came up to that was we wanted a high CL max wing for our hand launch so that our stall speed is much lower than it was initially. And we also wanted to design our aircraft to fly around a wing loading of about 65 units per meter squared. This is behind our maximum that we can hand launch at, which is about 70, so we have a little bit of a buffer either way. For our payload weight, we estimated it to be about 2 kilograms. Our payload isn't currently at 2 kilograms, it's actually less, it's about 1.4. There is some extra leeway to add more components down the line should we need it. And lastly, our empty weight fraction is about 0.6, which allows us to build the airframe to be as sturdy as needed. The power that we gained from this, the power loading that we got from this graph was about 5.5 from the wing loading of 65 units per meter squared, which gives us a thrust to weight of about 0.37 for 15 meters per second flight. Next slide, please. This is a little bit more constraint sizing, more on the wing sizing and our hand launch flight path. So our wing sizing was designed to place our L over D max at 15 meters per second so that we're as efficient as possible in cruise, because the objective of this aircraft is for endurance and range. We also designed it to reduce the stall speed to near hand launch speed, which is it's at 9 meters per second for stall speed, and our hand launch, if you remember, is 8 meters per second. So to overcome that, we require a thrust to weight of 0.6 to hand launch. And the bottom graph more or less shows how our flight will behave when launched from 1.7 meters. Next slide, please. Here we have our airfoil selection. When selecting our airfoil, we did a trade study of about 6 different airfoils. Each were compared at around number of 200,000. And we placed a lot of emphasis on our small angle of attack values, so anywhere from -5 to 5 degrees angle of attack. One of the main preferences of our airfoil was we wanted it to have a larger camber so that it would have higher lift at low speeds, again for that hand launch requirement. In addition to that, larger thickness aids in manufacturability, so that was also a plus. But of course, the main defining trait was the max CL/CD of each airfoil. So on the right, you'll see a few graphs of the different CD versus alpha, CL alpha, and so on the graphs. The airfoil that we ended up choosing was the MH114, pictured at the bottom left. And this is because not only did it have a good thickness, but it also had the largest camber amongst all the airfoils and produced a very good CL/CD alpha. Now, of course, the S1210 and the S1223 also produced very good results. However, the reason why we chose the MH114, if you look at the bottom left graph, which is the CM versus alpha, the MH114 has a much better stability balance in regards to its center of moment than the two Steeler airfoils. This would mean that we could get away with a smaller tail than with the two Steeler airfoils. So that's what inevitably led to our choosing of the MH114 as our selected airfoil. Next slide, please. For our wing design, we had a couple of different wing design options, and we did a plan form trade study. We examined 5 different options. We had the rectangular wing, tapered wing, elliptical wing, pointed tip, and sweep back. Of these 5, the first thing we wanted to look at was how easy or how reliable manufacturing is, so that if we needed to make a replacement, we would be able to do so on constrained time. The elliptical and pointed tip wings were eliminated because they were deemed too hard to manufacture or took too many resources to manufacture reliably. So the top three wings were the rectangular wing, the tapered wing, and the sweepback wing. These wings were modeled in XFlyer and compared at a Reynolds of 200,000, just like the airfoils. The dimensions were kept constant between all the wings, and the velocity was modeled at 15 meters per second. The graphs on the right kind of symbolize the performance of each wing with their CLCD max over alpha and their CL versus alpha. Quite apparently, the tapered wing has the greatest performance of the three, and despite being harder to manufacture than the rectangular wing, it's not very difficult to create one and create replacements if needed. Next slide, please. For our tail design, we again used XFlyer to model and kind of test out the tail design. We started with historical data and proportions to start with the basic tail, and then we used XFlyer to calculate our CM versus alpha graph, which is, we wanted to get a positive angle of attack, positive trim angle for our airplane. So by shifting around the size and distance from the wing, we were able to get a trim angle of about 1.2 degrees angle of attack. And of course, the negative slope denotes that it's relatively stable. For the airfoil itself, we wanted a symmetrical airfoil that won't produce any sort of lift moment. So we got the NACA 0012. With 12% thickness, it's fairly easy to manufacture and easy to implement. We do have an incidence angle of -1 degree on the tail, which helps us balance out our graph a little bit better. Next slide, please. Lastly, here's our stability analysis of the aircraft. From XFlyer, we were able to get the data that our mean aerodynamic chord was about 0.33 meters, and that our neutral point was 0.143 meters, with our tail configurations for the last slide. For the static margin, we wanted to stay between 7% and 10% because flight conditions for our aircraft are very stable, very normal flight conditions. So we wanted an aircraft that wasn't too twitchy or too muddled, so we decided to go the middle ground. So getting a static margin of 9% required a CG at about 0.112 meters from the leading edge, which is 34% of the mean aerodynamic chord. We're happy with our static margin. However, we want to do AVL analysis in the future to gain a little bit more information about the stability of our aircraft, in addition to what kind of forces we can expect from roll and pitch. Next slide, please. Here's a visual of how we want to do our CG balancing. The red dot is our CG and the green dot is our neutral point. One thing you'll notice from this is we want our fuselage, which we haven't finalized the design of, but we want our fuselage to extend down further so that we can do kind of like a two-layer setup of our internal components. So we would have our camera, GPU dev board, and our PIC-SOC all on one level, and then on the bottom level we would have our batteries which connect to our motors, which are mounted under the wings. This two-level configuration allows us to bring our CG forward and also provides a good space for our propellers because we are doing a belly landing, and propeller strike is definitely an issue that we wanted to focus on avoiding. Next slide, please.
So I just wanted to quickly just discuss this VN diagram. I really just want to pick off some of the important values that we get from it. You can see that the cruise speed was determined by the mission, so that was 15 meters per second. This VN diagram allowed us to determine a dive speed of 21 meters per second, a maneuvering speed of 14 meters per second, and a stall speed, which is very close to what Pratik has found with his aerodynamic studies of around 10 meters per second. And so that's what we've kind of got from the VN diagram.
So going over propulsion, for our battery, we chose to use a Venom 20C 3-cell 6400 milliamp hour battery. We used MotoCalc to calculate our values, and given a cruise speed of 15 meters per second, we have an endurance of 71 minutes, which is greater than what we required at 60 minutes. We also get an estimated range of about 64 kilometers. The current draw at takeoff is at 23.9 amps, which is probably going to be our largest draw throughout the flight, as we'll be flying at a pretty low speed cruising. And the max burst rate from the battery was 192 amps. We're planning on using two ESCs for our two motors, both of which are rated at 30 amps. So the max draw isn't an issue. Next slide, please. For the motor, we're going to be using two AXI AC2808-24 motors. The graph on the right shows the total efficiency versus airspeed, and we get our max efficiency at 15 meters per second, which is coincidental with what we wanted to fly at. The max thrust to weight ratio provided by the motor is 0.6, which is what we need for our hand launch, and the motor kV is 1190. Next slide, please. So for the propeller, we're using two propellers with our two motor configuration, one clockwise and one counterclockwise, so that way we can balance the torque on the aircraft. The RPM at 15 meters per second is 12,000, and we have a fairly decent propeller efficiency of cruise of 50.3%. Next slide, please.
So as a team, we were able to determine several of the risks that we feel will come up with this project. And as a team, we were able to sit together and determine mitigation strategies for these risks. You can see that they're ranked in consequence level and likelihood. But we feel confident in the mitigation strategies that we've come up with as a team. We feel we'll be able to avoid any of these problems. As for our budget, what you'll notice is that in the MCR we reported a budget of approximately $5,300, and that has now increased to $5,500. And the reason for this increase is, excuse me, the reason for this increase is mainly because of our processor study results. There were some extra costs that we found there. But that being said, we were able to reduce the cost of our avionics and our propulsion by 19% and 49% respectively. So with that, we still feel confident that we can maintain this budget, but we'll be aware of it moving forward. As for schedule, we are pleased to say that we've been on track with this timeline that we set for ourselves in the MCR, and we've looked over it again, and we feel confident that we can continue to maintain the schedule throughout the project. In conclusion, moving forward, we want to do some additional research in our camera choice so that we can find one that's optimal for for recognizing distressed people in these disaster environments. Further, we want to be cognizant of our budget moving forward so that we can take into account any payload cost increases. And that being said, we also want to do some AVL analysis such that we can get a better aerodynamics analysis there. At this point, I'd like to open it up to any questions that you guys might have for us.
Hey everyone, this is Stephanie on at Boeing. Had a quick question about your cost breakdown. I was wondering, have you guys looked at how much of that you can put towards testing versus your final product? And do you have a breakdown, I guess, of what you have for that? Oh, I don't think we hear you.
Yeah, sorry about that. That's a great question. We have a further breakdown on the MCR, but we honestly have not looked too much into the cost of testing versus the total aircraft construction. So that's something that we should look into more.
Okay, thanks.
Thank you.
Additional questions for the Team 4? This is Greg at Clemson University. On slide 9 and slide 10, you begin to talk about So these images are just sort of stock images in terms of image recognition, or did you guys do this?
So this is a YouTube video that our teammate Andrew downloaded off of YouTube, and then he actually used these pre-trained models to analyze that video, and then took a still shot of those videos while they're being analyzed.
Okay. Okay.
But in the next slide, these were videos that were actually taken by us from a fourth floor in the Georgia Tech building.
Okay. This is nice. It was a little bit unclear because this is not my area of expertise. You talked about GPU processing. So this does, and maybe I missed it. This is for real-time detection, or this is for stored detection, then related to GPS. How does this work?
Yeah, so to be quite honest, it's not my area of expertise either, but I'll relay the information as I understand it. So GPU is a graphics processing unit, so it's specifically catered for analyzing images and video. And so by running the CPU and the GPU in conjunction with each other, you can decrease the amount of processing time per frame. And so this will be real video that we're taking on our aircraft. It'll be analyzing it, and then when it identifies a person, we'll be able to send a still shot back to ground station with the GPS coordinate.
Okay, so could you go back then to your electrical diagram? There's a GPU on your plane?
Yeah, so we clumped that together with just onboard computer. So that'll be a CPU and a GPU.
Okay. How big is this? What does this look like, just out of curiosity?
Great questions. Let me see if I have that information for you.
We actually have a few supplemental slides at the end of the presentation that kind of go over that exact question. If you can just go to the end of the presentation, Nick. So this is an example of kind of the processors that we're thinking of using, as well as their dimensions.
Oh, okay. This is an assault on my senses here.
Fine.
Just a lot of information. Okay. Have you done any power calculation in terms of size of? You sized the battery out for your propulsion system. Have you considered the battery that you'll need to run this this GPU?
So currently, we're still finalizing our GPU and CPU kind of configurations. Once we have those figured out, we are definitely going to have an external power source. So we're going to look into that at a later date. But as of right now, no, we've only done the battery sizing for the aircraft itself.
Okay, so again, I'm not trying to dig into too many details. I would assume that you would need to run this GPU for the same duration as your flight?
Yes, that's correct.
Okay. And maybe the power consumed varies depending on if it's doing any processing, but I guess one would argue that you would always have to be doing processing of images?
Right. The CPU and GPU will most likely continually be kind of checking the video footage, see if there are any matches to the pre-trained software for if there was a person or not. So
okay.
That's definitely something, that's a great point. We definitely have to research that further in regards to what kind of power draw we're looking at and how this is going to affect our aircraft.
Okay. Yeah, so what would be really helpful for you guys, I think, would be to put together, similar to like your BOM you might be generating, you should probably do a power analysis on this as well, right? So your capacity of whatever your power source is will hopefully need to process or run not just your propulsion system, but also your computer, your onboard computer. Then you might need to look at current draw, but also voltage that these these GPUs process?
Absolutely. Thanks for the feedback. We're definitely going to look into that. That's one of our next steps, actually, is to kind of nail this down and then figure out all the specifics around it. But absolutely, we'll take that into account. Thank you.
Okay. Are there more questions, comments, concerns? Okay, I have another one then. Or maybe just an observation. Have you thought about the thermal management inside the fuselage of this aircraft and what that looks like in terms of your GPU generating some heat, your ESC generating some heat, your Pixar generating some heat, and how that's going to look within the within your fuselage? You might consider that or begin to evaluate that in testing.
Yeah, we haven't really begun to consider sort of thermal management. We have a rough idea of what our fuselage looks like. However, we don't have a modeled out model or anything near to a final design. So that's definitely something that we want to consider down the road when we have our fuselage completely designed, whether it's by spacing out the components or because our plane doesn't need to be weatherproof or anything like that. We might have small vents or something like that. But definitely something to look into. Thank you for bringing that up.
Okay, and could you jump forward to slide 24? Or backward, because we're on 33 right now. Okay, so 24 and 25, I think this is a plot of motor efficiency, and then maybe 25 is a plot of propeller efficiency. Is that correct?
Yes, I believe so, yeah.
Okay, so if you go back to slide 24, is the y-axis, is that total efficiency of the whole drive, or is that motor efficiency?
I believe that's motor efficiency.
Okay. So if I go back to Phil's and Carl's presentation on sort of propulsion, you just might think about how you're presenting the efficiency of the propeller, and then the efficiency of the motor ends up being sort of total efficiency of the propulsion system, right? So.
Yeah, we'll change that notation for the future. Thank you.
Okay. Are there more questions? I will yield the floor. More questions for Team 4. Okay. Well, I would like to thank those members who are still on the line for your feedback. If you have questions, comments, concerns, compliments for the teams that you were able to attend, please forward those to Kathleen Chang or myself, Greg Mako. If you are a Boeing or external member who has been here, hopefully you were shared the Qualtrics survey. If you can take a few moments to fill that out and give the team some feedback. Thanks, Team 4, for finishing us out strong here. Thanks to the coaches for attending. If there are no additional comments, I would close out today's PDR session. The videos for this we made available by the end of today. Thank you, Team 4. Thank you. Have a good Friday afternoon.
You too.
Okay.
Thank you.
Bye, everybody.
Bye.
Bye.